Okay, welcome to this next talk in the concurrency session. So our next speaker is Aleksandr, who will be talking about DafnyMPI. So welcome.
Thank you so much. Thank you for joining the session. So I will talk about DafnyMPI, which is a Dafny library for verifying message passing concurrent programs. And this research is joint work with Antero, Mejr, Sundar, and Jeff Foster. So I would like to start to briefly talking about MPI and what it is. So MPI stands for Message Passing Interface, and it is a standard that is widely used in high-performance computing, and it describes an API for C, C++, and Fortran, but there are libraries for other languages that also allow you to write MPI programs. And it is great in situations where you have highly structured communication. Such as in partial differential equation solvers. So at the bottom of the slide, you can see an example. This is a solution for the heat diffusion, PDE, and this yellow rectangle is supposed to be a heated area, and it is surrounded by cold purple area, and then as time progresses, the heat dissipates. And so, as you can imagine, this kind of simulation is very local in a sense that in order to determine the value at a given point at time t, you only really need to know a small area around that point at the previous time step. And that means that it's very easy to parallelize because you can assign each process on your computer a stripe of a domain or maybe a cell of a domain, and most of the computation process can perform by itself, and it only really needs to communicate along the boundary with the other processes. So a bit more formally about MPI, and specifically the setting that we target is we target the setting with no shared memory, which is very typical as a standard, right? Also no dynamic process creation. So outside of some edge cases, right? When you run MPI programs, you specify the number of processes that the program will use, and that number does not change throughout the execution. Now, a program can support different number of MPI processes, right? But once it starts executing, that number doesn't change. And a few more things that stand out is that in MPI, messages may run asynchronously with the initiating process. So a process can initiate 10 receives and 10 sends, then do some computation on the side, and then decide to wait on them in some particular order, right? And also messages can be of arbitrary size. So it's not just passing an integer, you can pass a matrix of values. And it's, as you can imagine, very easy to make mistakes when writing MPI programs. So our goal is to verify that such programs are deadlock-free, that they terminate, and also to show functional equivalence with a sequential implementation. Because intuitively, it's much easier to make domain-specific errors that are difficult to identify when writing parallel code. So if you can prove that your sequential implementation is the same as the MPI implementation, then you have assurance that your MPI implementation is also correct. Now, a lot of prior work that specifically targets MPI mostly deals with model checking approaches, right? And so they often restrict the input or even the number of processes that are running the program. So our goal is to not have that restriction. All right, so with this in mind, let me introduce our first contribution, which is DafnyMPI, and it is an MPI library for the Dafny programming language. A few words about Dafny. So Dafny is an auto-active verifier, so that means that it fills in low-level proof details for you. It enforces termination by default. You always have to prove termination, and it is great for proving functional equivalence. There's one problem. Dafny natively does not support concurrency, right? It's not designed for that. It's a sequential program verifier. So we want to use what it gives us, but we can't because we're trying to verify MPI programs. So in order to solve this challenge, we introduced a library. So it's not an extension of a language. It's code written in pure Dafny that you can just import. And it essentially makes MPI communication deterministic from the verifier's point of view. And it allows us to verify MPI programs by requiring the user to specify the communication topology upfront, and then requiring the user to satisfy preconditions on MPI API methods that DafnyMPI adds. All right. Let me show a small example, so a very simple MPI program. So here you have n processes, and they do the same thing m times, m iterations. So there's a loop, and something is repeated. And what is happening is that there's some computation that is local. We don't care about that. What we care is that process 0 sends a value to process number 1, and process number 1 sends a value to process number 2, and so on. Right? And then in the next iteration, the same thing happens. And then the next iteration, the same thing happens, and so on and so on. So if we want to describe the structure of this communication, like the whole program, the entirety of it, we really want some way to distinguish between the messages being passed. Right? And so the idea here is that we want to assign a unique tag to every message. Right? So that first message that process 0 sends to process 1 is going to be tagged as 0, for example, and then the message that process 0 sends in the next iteration is going to be n-1, and so on. And fortunately, you can do this in MPI. MPI allows tagging messages, although MPI does not impose the restriction that they should be unique, so we do. So in DafnyMPI, the tag for a message has to be unique. Why is this helpful? Right? Because if you keep this picture in mind, right, you can see that you can probably define the sender and the receiver of each message as a function of the message tag. And so this is exactly what we ask the user to do when they begin writing their MPI program. So they create this MPI world object, which is what you have to do in any MPI library. But in DafnyMPI, there are also some ghost arguments that the user has to fill in, such as identifying the sender and the receiver and the payload as functions of tag and size, right? Size being the number of processes and tag being the specific identifier of the message, right? So for the example that I just showed, you can just take the remainder of a tag by dividing it by the number of messages that are sent in each iteration, and that gives you the center, for example. And then after you create this object, the process may then query for its own rank and the size from that object, and these are uninterpreted. Everything that follows, so the code that follows, it cannot assume anything about the process's rank, right? So you can branch on it, right? And if you are in an if condition following some constraint on rank, then you can assume that. But otherwise, it's uninterpreted, and the proof has to work for that. And we also support collective operations. I'm not going to go into too much detail here in the interest of time, but we support barriers, gather, all reduce, and it's generally possible to add collective operations and interleave them with regular point-to-point messages. Now, how is this topology enforced? So anytime the user wants to receive or send a message, they have to call the corresponding method in DafnyMPI. And that method has preconditions, requires clauses in Dafny, that check that the receiver and the sender are just as they are specified, has been specified by the user originally. And also, if you are receiving, for example, then you also get a pause condition that allows you to assume that the value that that is being put into the destination array, destination matrix, that is exactly as specified by the user, right? It's a payload of a message. And there are also some other preconditions that ensure an ordering of message tags, because of course we're in a concurrent setting, so we want to prevent deadlocks, and so the idea is that the process must wait on increasingly larger tags, and that prevents deadlocks, and of course you also should not wait on a tag that you've already used before, and the tags have to be correctly intervened between the barriers. All right, so I've introduced DafnyMPI, but I haven't really talked about what we prove about it, right? So I've mentioned deadlock freedom, for example, but right, how are we sure that it's actually deadlock free? And also I haven't really talked about the programs you can write with DafnyMPI, so that's going to be what I will do in the next few minutes. So in order to prove properties about DafnyMPI programs, we introduce a core calculus that abstractly describes all the programs that you can write in DafnyMPI. And so it's an imperative language. It has some common control for all constructs that you can expect, conditionals, loops. It allows setting variables. Environments are local to the process. Importantly, there are 4 commands that are specific to MPI communication. So I receive, I send, wait, and barrier. So barrier synchronizes all processes, as we saw in the previous talk. But then we split receives and sends into 2 parts, as you can do in MPI. So there is an initial receive or immediate receive, and then there is a wait, and the same for send. The idea being that a process can initiate a message transmission or start receiving a message, but then do something else in the background, and only when it calls wait does it actually block until the communication is completed. And this first argument here for I receive and I send is the tag. It's an expression that evaluates to the tag of the message, right? So we don't even specify the sender or the receiver explicitly because we assume that we have these functions that the user provides that map a tag of a message to the sender, receiver, and the payload. So in the paper, and I encourage you to look at it for a more detailed description of this, we prove that for any program that you can write in our core calculus that also respects the properties guaranteed by DafnyMPI, there exists no reduction from the initial state to a deadlock state. Right, so for any command in the initial state, right, all processes execute the same command, regardless of what it is, you will not get to the deadlock state. Very briefly, the outline of the proof. So the idea is that you prove this by contradiction. You suppose that deadlock is reached, then you pick the process that is blocked on the message with the smallest tag. It, of course, has a communication partner, right, for that message. It's either sending that message to some other process or receiving from some other process. And then you can just look at that other process of the communication partner, and you see that whatever its state, whether it has terminated, is blocked, or is running, you actually get a contradiction. So a deadlock cannot happen. So something that is particular to our core calculus and specifically operational semantics is that we model some of the aspects of MPI quite closely, and so I want to highlight one of these things, which is the non-deterministic behavior of send operations. So in an MPI, you can have a send that completes before the receiver initiates the transfer of the message, right? So the way this works is that, so here is a timeline from left to right, it's time, right? So if a sender initiates a send, that message could then be buffered by MPI runtime. And so when the sender calls wait, it is possible for the sender to actually continue execution, and from its perspective, the message has been transmitted. Even though the actual transmission of the message happens later when the receiver calls receive. But as I mentioned before, in MPI you can transmit very big messages. And so in fact it's quite possible that MPI runtime cannot buffer the entire message. And so in this case actually the sender does block, right? And it will have to wait until the receiver calls by receive on its own end. And only then will the message be transmitted and both processes can unblock. Right? And so our operational semantics allows for both things, and so the proof works for both things. All right. Okay, so a few words about limitations. Right, so we don't support some things in the MPI. I'd say it's a very big standard. So we don't support wildcard receives. So a receive always has to have a specific source, right? The message has to come from a specific source. You cannot receive from an arbitrary source. And we also do not support multiple communicators. So that means that all collective operations have to work for all processes, right? So if you have a barrier, all processes wait on that barrier. And also we model collective operations as barriers in the core calculus. So if you've seen if you remember core calculus that I showed, it only has a barrier as a collective operation. Now, from the perspective of a deadlock freedom proof, it doesn't matter whether it's a barrier or some other operation. But of course, for the library itself of DafnyMPI in order to support gather. For example, we add additional specifications that are not reflected in the core calculus in order to reason about the output of those operations. Right, so now let me move to our third contribution, which is a set of free verified partial differential equation solvers that use MPI. So these are solvers for the linear convection, Poisson, and heat diffusion PDEs. So the linear convection models the transmission of a wave to sort of a constant speed, and so you can see the communication topology for it at the top left. This is what I've showed you earlier. So Poisson has a bit more complicated communication structure because each process has to communicate both with the process on the left and the process on the right, and entire rows of data are being sent. Right, so here it's columns, but it's transposed for visibility. But so entire rows of data are being transmitted, and also in the end there is a convergent criteria. So there's a check after each iteration to determine whether or not the convergence has been reached. The last one, the heat diffusion, is in some sense the most complicated one, because in this case entire matrices of data have to be transmitted between processes, and these matrices can overlap. So for example, we support a situation where a process sends chunks of data to the process on the right and process on the left, and it actually sends some of the data to both, right? So this overlap here in the middle. All right. Aside from implementing these PD solvers using MPI, we also implement sequential versions of these, and we prove them to be functional equivalent through bitransitivity with a functional specification, right? So the idea is that you write the sequential implementation, and that is the one that's easiest to proofread. You can show it to a person who knows really well how to write partial differential equations code, and they can read it and check it, essentially. Then there's a functional specification, which is, at least subjectively to me, much more difficult to read, but it's definitely much easier to write proofs about, right? And then there is the MPI implementation, which is the most efficient and the most difficult to reason about. So the idea is that you take a functional specification and you prove it to be equivalent to both sides. A little bit about evaluation. So we've actually compiled all of the code that are written to Python and run it with different number of processes. Right. So here, for each of the three benchmarks, you can see a graph that shows the running time as a function of the number of processes, and you can see that it goes down. So the first point here is the sequential version, and then all the subsequent points are the MPI version with different number of processes. So that shows that the programs that are written, they're not just functional equivalent, they don't just deadlock, but they actually do give us a performance boost. And this jump at the end that you see seems to be specific to the machine that we ran this on. One of the artifact reviewers didn't see that, for example. So the main trend is that it goes down in the beginning. So another thing that was particularly interesting to me is to measure the percentage of ghost code, right? Essentially a verification overhead or a proof complexity metric, if you will, right, for these programs. So here you can see for every benchmark and every part of the benchmark, so specification, the sequential part, the parallel part, and maybe some shared code that's used by both implementations, you can see the number of lines of code and also the percentage of ghost code. So the percentage of code that's not compiled, that's only used for a specification. And of course it's much higher, that percentage is much higher for parallel versions. Even though a huge amount of proofs of a proof is completed automatically by Dafny, right? So these specifications are only really necessary when you deal with some gnarly modular arithmetic, for example, and you need to guide the verifier. All right, so to summarize, we describe an approach for introducing MPI concurrency into sequential program verification context, and we implement this specifically for Dafny as a DafnyMPI library. we prove that DafnyMPI library guarantees deadlock freedom by enforcing an ordering and message tags. And we use DafnyMPI to verify free partial differential equation solvers, including proving equivalence between the MPI and sequential implementations. And you can read the paper, and I will be happy to take any questions. Thank you.
Thank you, Aleksandr, for the talk. Any questions? I see Joe there.
So in these examples that you did the functional equivalence verification for, are they using floating points for these calculations? I assume PDE solvers need floats.
Right. So this is yeah. So in Dafny we use reals, and so we don't model any. If that's your question, right? So we don't model any kind of hardware specific issues that can arise from floating point computations, right? So that would be an entirely different line of work. But yes, the idea is that once you compile them, they do, yeah.
Hi, one thing I'm curious about, the starting point, just the setting for the work, is this very structured message passing setting, right? It's like statically I can predict exactly the messages that are sent, I can give a unique tag to every message. I mean, I wonder if you could just maybe speculate a little bit about it, maybe you've thought about it a little bit, like pushing this idea a bit further. Can I do data-dependent message passing, where whether or not I send a message depends on a certain data condition? I mean, this could be, for example, a sparse solver. You only send a message if you actually have a non-zero at some position. These sorts of tricks, significant improvements in message volume, you can get significant performance improvements, right? I don't know, have you thought about these kinds of settings, and would the technique scale to these as well?
Right, so thank you for this. So yeah, so this is definitely a direction for future work. I think the closest to what you're saying, which is a bit simpler, but still is what we did for Poisson, which is that so there is a convergence criteria, and you don't know, for example, the number of iterations a priori, right? And so at the end of each iteration, each process decides based on the output of the all reduce operation, which checks the convergence criteria, so it decides whether or not to continue execution. So it is data dependent in that sense. And yes, of course, in the future, I think an interesting line of work would be to explore these more complicated settings. So this is what we want to do, but still work in progress, or in future work. Yeah.
Hi, thanks for the talk. One of the interesting things about MPI is that it has both blocking and non-blocking versions of a lot of different communication primitives, and they're actually allowed to intermix, so that you can have like a blocking receive matching with a non-blocking send, etc. Do you model that at all, and how do you reason about that?
Yes, so we do have, well, to be precise, we model the immediate send, and immediate receive, and blocking sends and receives, and it is entirely possible for one process to use a non-blocking version, an immediate version of a send, for example, and the other process to block on the receive. So there's no restriction in that sense. The way we model them is, right, so in the core calculus, we differentiate between the beginning of a receive or send and the wait, which is where the block can happen. And so if you want to write a blocking send or receive, you simply follow a receive by a wait or send by a wait. But you're allowed not to do that. You can like have a ton of different computations and other communication operations in between, right? The specific way we model this is by explicitly modeling the buffer. In our operational semantics, we keep track of the sort of internal MPI buffer, and that allows us to say that a receive can, a send can transfer a message to the buffer, for example, in the background while something else is being executed. Yeah. So that was sort of one of the main motivations, is to support non-blocking receives and sends.
Okay, any final question? Okay, then my final question is, like, you have your core calculus and you have all the stuff in Dafny. How do you make sure that these things are related?
Sorry, related to, could you repeat it?
So there's the core calculus, and you have the actual implementation in Dafny.
Right.
How do you make sure that the Dafny implementation corresponds to the semantics of your core calculus?
Right, so we don't, right, that's a simple answer. It's fairly small, right? The trusting base of the library is fairly small, so I think that's one way to have some confidence of that. In the future, I think there's definitely space for mechanizing both the deadlock freedom proof and potentially this connection that you're talking about. So that could, of course, be part of future work, yes.
Yeah, that would be interesting to do. Let's thank the speaker once more.